All right, so as I've kind of alluded to and concluded the last video with, hemoglobin's a little bit of a different animal. It's a tetramer. It's made of four subunits, and each one of those subunits is capable of binding O2. Each one of those subunits has a heme molecule that is coordinated that binds O2. So the composition of a protein ligand complex for hemoglobin is a little bit different, and the stoichiometry is different from that of myoglobin and binding to O2. So let's go ahead and get cracking at that. If you look on the left and the right hand sides at the top of the figure here, what we have are the two different model representations for hemoglobin. And at first glance, they're kind of similar to one another. But what I want you to do to focus in on the subtle differences is that if you look on the model on the left hand side, it's kind of got a bluish green, a sea green type of appearance to it. And what I want you to do is look at that central cavity. This central cavity is that big. Now, it might take a fine look and zooming in on it. I think I can zoom in. Did it yesterday by accident. Look at that, and we compare it to that opening. So these two openings are slightly different in size. Zoom too much. That is significant. These central cavities have different they occupy different amounts of space and they coordinate different things. So this model on the left-hand side is actually the deoxy hemoglobin. And this is on the right-hand side, the oxy. Another thing that I'd like to draw your attention to is, as an example, we can use this, I think that this heme structure right here versus this, I have this stylus, which it seems like it disappears on the screen. There we go. If we look at the proximity of those two heme with respect to this blue helix, you can see that there's a little bit of space between the heme and the helix. Then if we go over to this one, you can see that the helix is behind, or sorry, the heme is behind that helix. Now, those are very minor, subtle differences. They are significant because what they're showing is that these proteins undergo very, very minor changes in shape. Just as we talked about protein structure, a protein is a kind of breathing organism. It's not an actual organism, but it's a breathing thing, it's a moving thing. Well, hemoglobin is a great example of that. Hemoglobin has two stable states, the T state and the R state. The T state is your deoxy state. This is also known as the tense state, and the R is the oxygenated state. This is known as the relaxed state. Oxygen can bind to both of them, but has a higher affinity for the R state. So that might sound a little bit counterintuitive, but the R state is more likely to hold on to oxygen than the T state. So that deoxygenated form, it's not kind of needy and it's not clingy. It's not like, oh, I need oxygen desperately. Instead, it says, yeah, I'll bind some oxygen. Whereas the R state, the one that already has some oxygen, it's almost like, I don't know, I feel like there's a metaphor or there's an analogy for like, you know, rich person or something like that. The R state has oxygen already, but it wants to bind it more and it wants to hold on to it. Whereas the T state version, take it or leave it. The absence of oxygen in the T state is going to predominate. So the T state is the conformation of deoxyhemoglobin, and the R state is the conformation of oxyhemoglobin. And it's whenever the T state begins to bind oxygen where these very minor changes take place and we transition from the T state to the R state. Looking at those differences, for some reason, I always think about like plastic surgery. I've watched a lot of reality TV in my life where there's, either a show about plastic surgery or a show where someone gets plastic surgery, like a facelift or something like that. And the differences are very minor. They're movements like, a facelift is not like I'm going to pick up your eyebrows and put them on your forehead or the middle of the top of your skull, but instead they're very minor movements where oh, well, this piece of skin, what I'm going to do is stretch it out 1 millimeter so that there's not that wrinkle underneath your eye. So that's kind of what happens whenever we talk about protein structure changes. Now, another representation of this is shown here, where we have the central axis and these subunits rotating ever so slightly. Now, I don't want you to look at this and say, oh, it's a 15-degree move or anything like that. But instead, what I want you to kind of visualize and think about and process is for a protein to change from, or for hemoglobin to go from the deoxy state to the oxy state, there are these very, very minor movements. And those minor movements are caused by individual atoms, like an O2 molecule, two oxygen atoms, inserting themselves and causing a subtle change here, which causes a subtle change here, which causes a subtle change here. And in time, the structure of that protein fundamentally changes. So, the structure of hemoglobin, mammalian hemoglobin is an alpha 2 beta 2 dimer. So it's two alpha subunits, two beta subunits. And this is also known as a alpha beta dimer, or sometimes referred to as a dimer of dimers. It's an overall tetramer. And here what we see is the alpha subunit and the beta subunit interacting with one another. The alpha beta dimers, which are depicted here, associate through hydrophobic and ionic interactions as well as hydrogen bonds. So those overlaps, those are your hydrophobic, and ionic interactions that stabilize those contacts there. The dimer of alpha beta dimers associate through ionic interactions and hydrogen bonds. So ultimately, what we have is we have these sort of a dimer formed with hydrophobic, ionic, and hydrogen bonding. And then the dimer of dimers is through ionic and hydrogen bonding. So the ionic and hydrogen bonds can be disrupted with pH changes. So we can go from a tetramer to two dimers if you adjust the pH or adjust the salt concentration. But no matter, not, I'm not going to say no matter how much, but those hydrophobic interactions are going to remain intact almost regardless of the pH adjustment. So if you adjust the pH, you're going to go from a tetramer to two dimers. Continue adjusting the pH, and you're going to stick with just two dimers because those ionic and hydrogen bond interactions, those are going to be disrupted, but the hydrogen bond interactions are not going to be. So pH will disrupt the tetramer, but not disrupt the two dimers, Now, here what we see, and I'm going to show this for the R state as well, the T state is stabilized by a series of ion pairs that lie at the intersection between the alpha beta protomers. So here what we have is basically the contacts between different amino acids and different parts of our protein. What I really want to draw your attention to is, we've talked about ionization of amino acids, histidine, for instance, having a positive charge, aspartic acid having a negative charge. This is illustrating, well, we have a ionic interaction between a strand and itself. We have an ionic interaction between two separate strands, another ionic interaction. We have an aspartic acid and arginine that are interacting with one another, histidine and an aspartic acid that are interacting with one another, the C termini and a lysine. Key word there, or the key is that this is the C termini and a lysine. That is not a secondary structure because it is a backbone interaction and an R group interaction. A backbone R group interaction is a tertiary state. So I'm going to move past this one, but the T to R transition, oxygen binding initiates a series of movements that result in the shift from the T to the R state. So some of those interactions that we established previously, they get disrupted or rearranged. And ultimately, we get a movement from what's shown on the left-hand side to the right-hand side. I think that this model illustrates that central cavity closing in a little bit better because of the fact that, well, the proteins are next to one another and they're same color. The movement is going to affect predominantly the quaternary structure of the alpha beta protomers and lead to ultimately this R state. Now, what I want you to recognize is between the T state and the R state, that central cavity is completely exposed for the T state, but then for the R state, it's kind of occluded, it's kind of like it's shrank down and it's kind of blocked off by, if you look at that histidine HC3, that histidine there is going to be blocking that off. All right, well, I'm going to stop for this video and I'll catch you in the next one.